Kia ora and welcome to video 20 in the series Insightful Integration. This video is similar to the previous one, except a lot trickier. So in the video released yesterday, we saw a recursive integral formula. This one here doesn't involve trig anymore, but it's more difficult, the structure of it. The first question itself, finding I1, is not too nasty, and in doing so, it gives you kind of a hint to how to solve part 2, which is nasty. And then, like I was saying in yesterday's video, finding I5 can be found using the recursive thing that you've proved in part 2. So I5 would relate to I3, I3 would relate to I1, of which I1 you've found in part 1. So the problem is definitely a difficult one. On the scale of 1 to 5, it's up there. All the best in solving this, and we'll catch you after the intro music for the solution, and then next week the last 5 videos of the series.
Alrighty, this problem is pretty challenging, as I said at the outset. The first part of the question, I1, is a pretty standard integral. You can see it in an NCA paper. The second part needs integration by parts because of the nature of this integral being a product, and it also has a little bit of a trick to it. And then the third part requires you to use the formula in part 2 over and over again. So it's another example of a recursive integral where one of the integrals depends on a previous one. Alrighty, let's get cracking. So first up, I1, when n is 1, we're integrating between 0 and 1, x, 1 minus x squared dx. Now, a basic substitution will work in this case because the inner function's derivative appears in the problem, almost. So my little trick here is I like to make the derivative in the problem, so times by minus 2, and then if I divide by minus 2 or multiply by minus 1/2 on the outside there, I haven't changed the integral at all, but I've made it easier when it comes to making a substitution. You could just use reverse chain rule if you want, or if you're not confident with that, if you make u is equal to 1 minus x squared, then the derivative, as I said, now appears in the problem, and so we're actually integrating. Again, I'll leave the limits till later. We're integrating u to the half du. Okay, this minus 2x and this dx is the du part, and then we've got the square root of u, which is u to the half. Now the limits, when x is equal to 0, u is equal to 1, and when x is equal to 1, u is equal to 0. So our limits flip around, which looks a little bit strange to have the top limit lower than the bottom. It's not an issue. We're not finding an area or anything, but what we can do is flip them back around and get rid of the minus that sits in the front. Because if we integrate something backwards, we'd get the negative of if we're integrating it forwards. Okay, so that equals u to the 3 over 2 divided by 3 over 2, or times by 2/3, between 1 and 0, multiplied by 1/2, and that comes out to be 1/3. Okay, so pretty straightforward start. It was a problem that required the reverse chain rule. Now this next part, show that if n greater than or equal to 2, in equals this fraction multiplied by in minus 2. So we work on in now, the evil integral that it is. In is the integral between 0 and 1 of x to the n root 1 minus x squared dx. And this is a really, really neat question, but it has got an insightful trick to it. And that is, we need integration by parts. I chose not to put that hint in the problem. I have covered integration by parts in an earlier video in the series, but I wanted you to recognize that there is a product of two things here, and they don't simplify. A simple substitution is not going to help us in this case because of the n. So what we do, remember integration by parts is the integral of fg dash with respect to x is equal to fg minus the integral of f dash g dx. So what do we choose? originally I chose this to be f and this to be g dash, and then I realized, well, that was silly because I don't actually know how to anti-differentiate this dude here without any trig substitution. Like it's messy, and it can't be that messy. So I went back to the problem and tried it the other way around, and I'm like, okay, cool, I know how to diff this one. So if I made this f, that would be okay, but then I'm going to make this g dash, and therefore my integral on the right is going to get worse because it's got a g in it, and that would make it x to the n plus 1 over, and the n's are going to go up rather than down, and I want them to go down because there's an n minus 2 in the right hand side. So it looked like both methods weren't going to work for me. So what I did is I went back to this first part, and this is actually a hint in here. The first part, the integral worked really nicely because there was that x sitting there in the front, which was related to the derivative of the inner function. So this is the insightful trick you need for this next part. What we're going to do is rewrite this integral as x to the n minus 1 times x. Okay, because when you times those two things together, you get x to the n multiplied by 1 minus x squared dx. I'm also going to put the minus 2 in like I did earlier, and I don't know why I left a massive gap there. It's going to annoy me, so let's move it across. But I put the minus 2 in there, and then I put the minus a half on the outside like I did earlier. And now we've got it perfect for integration by parts, because I'm going to make this dude here the f, and I'm going to make this dude here the g dash. I know how to anti-differentiate it now because I've just done it. Except when I did it earlier, I wrote it in terms of u. So this was the answer here. And I'm going to have to write that in terms of x. Okay, so integration by parts. Oopsies, I lost the formula for it. So we've got fg minus the integral of f dash g. Well, f is x to the n minus 1, so f dash is equal to n minus 1 x to the n minus 1 x to the n minus 2, and my g, the antiderivative there, is equal to 2/3 1 minus x squared to the 3/2. Differentiate that using chain rule. The 3/2 will come down and knock the 2/3 away, so make it equal to 1. The power will drop to a half, and then we'll get a minus 2x factor, the inner function differentiated. So that's perfect. Okay, therefore the integral minus 1/2 times 5. I'm just going to ignore the limits for now. Okay, the limits between 0 and 1, I'm going to ignore it, just find the antiderivative. So I've got x to the n minus 1 multiplied by g and then I've got minus this new integral, which supposedly is easier, f dash g n minus 1 x to the n minus 2 multiplied by 2/3 1 minus x squared to the 3/2. Now it looks like the problem's got harder, but there is a little trick to it. Remember that we're not trying to actually work out what this integral is. We're going to try to work out how it depends on another integral in this sequence. Okay, now in terms of subbing in the limits, what I would need to do is I need to work out this antiderivative and then sub in 0 and 1 into the whole thing. But there's a shortcut for definite integrals. What you do is you evaluate this dude here between 1 and 0, and then you integrate this part here between 1 and 0. And the reason why I'm going to do that now is because that first thing, also bear in mind that there's a minus 1/2 in the front, but the first integral actually becomes 0. Okay, if you sub in the upper limit, which is 1, into the function x equals 1, then this whole thing's going to be 0. This bit here is going to be 0. And then if you sub in the lower limit of 0, this dude's 0. So that whole first part of it is 0. And then we're minusing an integral between 0 and 1 that looks messier. But there's another trick that will help us get our result. Don't know why I rewrote all of that again. Okay, we've got a minus a half at the front and another minus, which makes a positive a half. We've also got a 2/3 factor in there, which we'll pull out to make a third. And then we've got an n minus 1, which is a constant we can also pull out the front. So we've got a third n minus 1 multiplied by this integral, which looks kind of similar to what we've seen before, just a slight difference. Remember that this is all equal to in. If we go back up to what in actually is, it's got x to the n, and then it's got 1 minus x squared square rooted. What we've ended up with is very similar, but we've got 1 minus x squared to the power of 3 over 2. So here comes the trick. That's why I guess this is called an insightful problem. If we write this x to the n minus 2 thing, we leave that. If we write this other bracket, 1 minus x squared to the power of a half, which is the square root and what we want, multiplied by 1 minus x squared to the 1, which is just 1 minus x squared, we can now expand some brackets. Okay, we can write x to the n minus 2 times root 1 minus x squared. That's the first part. If I take all of this and times by 1, and then I do the second thing, all of this times by minus x squared. When I do that minus x squared thing, I get x squared times x to the n minus 2. Right, this term times this term becomes x to the n minus x to the n and 1 minus x squared square rooted. Integral of a difference is the difference of the integrals. So, and the structure of these integrals have both got a 1 minus x squared square rooted in it. So that first one is in minus 2 and the second one is in. So we've got 1/3 n minus 1 all times in minus 2 minus in. And now we just need to solve for in. It's like a linear equation. We move, we've got in already on the left hand side with a 1, and then we take away, no we don't take away, we add 1/3 of n minus 1 to it. I'm moving this dude here, expanding it, moving it to the left hand side, and then left on the right hand side is 1/3 n minus 1 times in minus 2. Okay, now I'm going to times everything by 3 just to get rid of the fractions. 3 plus n minus 1 equals n minus 1 times in minus 2. And then on that left hand side, that bracket is 2 plus n. I can divide that out and put it on the bottom of the other side. N plus 2 or 2 plus n, in minus 2, and there we go. We've proved the result. How cool is that? And the last question asks us to find I5. Now the cool thing about these recursive sequences, and I think I mentioned this in problem 19 when I went through it, is if I want to find I5 using the definition, I would have to find the integral, this integral here, I believe, right? We'd have to go back to the definition of in and just replace n with 5. But that integral there is pretty evil to find. Like, it's not going to be a simple substitution to solving it. And we'd have to use integration by parts repeatedly to reduce this down till it got to x, so therefore I'd be able to anti-diff it. Now that's a bit pretty evil, but we've got this new iterative formula now. I5 is just 5 minus 1 over 5 plus 2 times I3. Okay, so what does that equal? 4 over 6. 4 over 6, or 2/3. No, gosh, 5 plus 2 is not 6. 4 over 7 times I3, which is 4/7 times, then we're going to use the same formula again. We're going to replace the n with a 3. So we've got 4/7 times 3 minus 1 over 3 plus 2 times I1. 3 minus 1 is 2, so we've got 2/5 there. In total we've got 8 over 35 times I1, and then I believe we've already worked out I1 earlier. I1 was equal to 1/3, so we've got 8 over 35 times 1/3, and that comes out to be 8 over 105. And the cool thing about definite integrals, if you hadn't realised, you can solve them on your graphics calculator. So if you wanted to check that answer, all you'd need to do is go to the definition of in, replace n with 5, and then solve the definite integral on the calculator and get 8 out of 105. A really good way of checking your answer. If the problem wasn't a definite integral, you could just make up some random limits, substitute those limits into your antiderivative that you thought was the answer, and check if your substitution matches what the calculator gives you. It's a nice little hack to check that you've got something right. It is frustrating though if they don't match, because it means either your substitution's wrong or, worse, your antiderivative's wrong. Hopefully you enjoyed that problem, and hopefully the series is proving helpful for you. There are 5 more questions to round off the series next week. Catch you in the next one.